Hello everyone, welcome to the course on basic electronics. So the course code is 23ECT23B. So myself Amayas, Assistant Professor Department of ACE. Today we'll discuss about module 3 and its module 3 is all about integrated circuit operational amplifiers and its applications. So these are the content. Integrated circuit operational amplifiers, where we'll get to know about the basics of the operational amplifiers. Biasing operational amplifiers, like how the op amps are biased, voltage follower circuits, non-inverting amplifiers and inverting amplifiers, and some of the application circuits related to operational amplifiers like summing amplifiers, differential amplifiers. First we'll start with the integrated circuit operational amplifiers. Operational amplifiers, or it's also called as op amps, they are commonly called as op amps, and these are one of the basic building blocks of analog circuits. They're extensively used in signal conditioning, filtering, or to perform mathematical operations like adding, subtraction. It can be used as adders, subtractors, integrators, differentiation. So all these are applications of operational amplifiers. So an operational amplifier or op amp is fundamentally a voltage amplifying device designed to be used with external feedback components such as resistors and capacitors between its input and output terminals. So these feedback components determine the resulting function or operation of the amplifier, and by virtue of the different feedback configurations, whether resistive, capacitive, or both, so this amplifier can perform a variety of different operations, which gives rise to its name as an operational amplifier. So that's why the name is operational amplifiers. So here we can see the block diagram for operational amplifier. So which is consisting of two inputs. One is non-inverting input and the other one is inverting input. That is given to the input stage, where the dual input balanced output differential amplifier. It acts as a differential amplifier. So the output of the input stage is given to an intermediate stage, where it is acting as an output differential amplifier, which is an dual input unbalanced output differential amplifier. So the output of the intermediate stage is again fed to the level shifting stage. Here this level shifting stage, at this stage it is acting as emitter follower, like with constant current source. So there should not be any variation in the current, and then that is fed to the output stage, the complementary symmetric push pull amplifier, and then we'll get the output. So here we can see the symbol of the operational amplifier, which is consisting of two input terminals, inverting input terminal and the non-inverting input terminal, and two supplies like V plus and V minus, and one output terminal. So from this operational amplifier is basically a three-terminal device which consists of two high impedance inputs. One of the inputs is called the inverting input, that is marked with a negative or minus sign. The other input is called the non-inverting input, which is marked with a positive or plus sign. So basically an operational amplifier is a high gain amplifier circuit with two high impedance input terminals and one low impedance output. The inputs are identified as inverting and non-inverting input. The basic circuit consists of a differential amplifier input stage and an emitter follower output stage. The voltage gains of integrated circuit operational amplifiers are extremely high, like typically around 200,000. Because of this high voltage gain, externally connected resistors must be employed to provide the negative feedback. So the design of this IC op-amp circuits involves determination of suitable values for the external components. The design calculations are usually much simpler than for discrete component circuits. So coming to this integrated circuit operational amplifiers, so this figure shows the triangular circuit symbol for an operational amplifier. So as shown, there are two input terminals, one input, one output terminal, two input terminals and one output terminal, and two supply terminals. The inputs are identified as the inverting input and the non-inverting input. A positive going voltage at the inverting input produces a negative going voltage at the output terminal. So conversely, positive going voltage at the non-inverting input terminal, it generates an output which is also a positive going, that means non-inverted. So plus or minus supplies are normally used with op-amps, and so the supply terminals are identified as plus VCC and minus VEE. So the two typical op-amp packages are shown in the figure B and C. For both the dual inline plastic package and the metal can package, terminals 2 and 3 are the inverting and non-inverting inputs respectively. 6 is the output. Pin 7 and 4 are the positive and the negative supply terminals. So coming to the basic internal circuit, the basic circuit of an IC operational amplifier is shown here. So the actual op-amp internal circuitry is much more complex, but the differential amplifier input stage has two high impedance input terminals and the emitter follower output stage has a low impedance. An intermediate stage between the input and output stages is largely responsible for the op-amp high voltage gain. Here it shows a BJT input stage while the other figure has a FET input stage. The op-amps that exclusively use BJTs are termed as bipolar op-amps, and those that uses a FET input stage with BJT additional stages are referred to as bi-FET op-amps. So here we can see the pin diagram for IC741 operational amplifier with the pin configuration and the pin diagram. So here the power supply pins, pin 4 and 7. 4 and 7 are the negative and the positive voltage power supply terminals. The power which is required for the IC to function, which is received from both these pins. The voltage level between these pins can be in the range of 5 to 18 volts. The output pin is pin number 6. So this output is delivered from the IC 741 op-amp is received from this pin. The output voltage that is received at this pin is based on the feedback approach that is used and the voltage level at the input pins. When the voltage value at pin 6 is high, this corresponds that output voltage is similar to the positive supply voltage. In the same way, when the voltage value at pin 6 is low, this corresponds that output voltage is similar to the negative supply voltage. So input pins pin 2 and 3, these are the input pins for the operational amplifier. Pin 3 is considered as the inverting input, while pin 3 is considered as non-inverting input pin. So the voltage value at pin 2 is very much greater than pin 3. which means that inverting input has a high value of voltage then the output signal is low. So in the same way, when the voltage value at pin 3 is greater than the pin 2, so pin 3 is a non-inverting input, pin 2 is a inverting input. This means that non-inverting input has a high value of voltage than the output signal is high. Then comes the offset null pins, that is pin 1 and 5. So this operational amplifier has an increased level of voltage gain. Because of this, even minimal variations in the voltages at both non-inverting and inverting inputs, those are happened because of the abnormalities in the constructional procedure or other anomalies will show an impact on the output. So in order to overcome this, an offset value of the voltage to be applied at pin 1 and pin 5, and this is generally accomplished by a potentiometer. Pin number 8 is not connected. It is just a pin that is used to fill the empty pin in the IC741 op amp. So it has no connection with any of the internal or external circuits. This diagram shows equivalent circuit of an ideal operational amplifier. An operational amplifier only responds to the difference between the voltages on its two input terminals, known commonly as the differential input voltage, and not to their common potential. Then if the same voltage potential is applied at both the terminals, so as a resultant output will be zero. An operational amplifier's gain is commonly known as open loop differential gain, and it is given by the symbol A0. So this diagram shows the two input terminals. It shows the virtual ground concept where we have this Zn. It is connected to the both input terminals, which helps us to understand the virtual ground concept. And here we have this gain. So the output of the op amp is always a product of open loop voltage gain as well as the differential voltages, that is input voltages. So here Z out is the resistor or impedance that is connected to the output. Some of the op amp parameters and ideal characteristics are open loop gain. So it is infinite. The main function of an operational amplifier is to amplify the input signal, and the more open loop gain it has, the better. So open loop gain is a gain of the op amp without positive or negative feedback, and for such an amplifier the gain will be infinite, but typical real values range from about 20,000 to 200,000. The input impedance, that is Zin, input impedance is infinite. Input impedance is the ratio of input voltage to input current, and it is assumed to be infinite to prevent any current flowing from the source supply into the amplifier's input circuitry. Real op amps have input leakage currents from a few picoamperes to few milliamperes. And output impedance, Z out. So Z out, output impedance must be 0 as an ideal characteristic. The output impedance must be 0. So acting as a perfect internal voltage source with no internal resistance so that it can supply as much current as necessary to the load. This internal resistance is effectively in series with the load, thereby reducing the output voltage available to the load. So real op amps have output impedances in around 100 to 20 kilo ohm range, but ideally the output impedance must be assumed to be 0. Coming to the bandwidth, bandwidth should be infinite. For an ideal operational amplifier should have an infinite frequency response, and it can amplify any frequency signal from DC to the highest AC frequencies. So it's therefore assumed to have an infinite bandwidth with real op amps. The bandwidth is limited by the gain bandwidth product, that is equal to the frequency where the amplifier's gain becomes unity. Next is offset voltage, that should be 0. So the amplifier's output will be 0 when the voltage difference between the inverting and the non-inverting inputs is 0. The same or when both inputs are grounded, real op amps have some amount of output offset voltage.